Hello everyone. Today we will see the Coulomb's law, which is in vectors form. Vector notation. As we all know, Coulomb's law gives the relation between the force and the charges and the separation between them. So we have F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square, where R is the distance of separation between the 2 point charges Q1 and Q2 and F is the force exerted between them. Now how do we represent this in vector notation, which is very important. As I have already told in my previous video, in order to know the vector notation, we just have to introduce the unit vector n cap. It is nothing but vector n divided by magnitude of that vector. So if we know this one whose magnitude is unity, which gives the direction of that vector, so now we can now write the Coulomb's law in vector form. It can be written as vector F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square into R cap. You can also write it as magnitude, no problem. So this gives the direction of the force exerted by between the two charges. Suppose I have two charges. I tell it as Q1 and Q2. Say that this is R1, radius vector, R2, we will take it as point O. Now force on this charge Q2, F2 due to 1 will be in this direction. This will be R21 and this will be F12. Force on charge, point charge Q1 due to Q2. Now if these two charges are positive in nature, then this will be repelling. The force will be repelling because it is one of the properties of the charges. Like charges will always repel each other and unlike charges attract each other. So now if F12 and F21 are positive and negative, then force will be in this way closely. So it is attraction in nature. How can I write this F21 in vector form? So vector F21 is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R21 square into R21 cap. This is the unit vector R21. So it is along this direction if these two are positive. So it is repulsive in nature. Now if it is F12, it is 1 by 4 pi epsilon naught Q1 Q2 by R12 square into R12 cap. It is in the other direction, or we can also write it as F21 is equal to minus F12. Now Newton's third law will hold good, correct? So they are equal but they are in opposite in direction. So this is how you write the simplest form of Coulomb's law in vector notation. Unit vector is very important and then this vector, this arrow mark you have to mention. So F21 will be equal to minus of F12. Okay. Now dealing with the multiple charges. Suppose I have three charges, multiple charges. Say that this is Q1, Q2 and Q3. How will I deal with this? The force experienced. At this point P, I have to mention the vector notation. So on this point, so when I consider this point P, say that you have a charge Q. So using the superposition principle, it is that force on this charge will be due to Q1, it also due to Q2 and also due to Q3. So when you consider this charge Q at point P, you have to consider all the three charges according to the superposition principle. So now comes the concept of superposition principle. It is same as the additivity nature of the charges. So when you consider the superposition principle, you have to consider one at a time and the effect of all other charges on that charge. So this is what the superposition principle. Same as how you have studied in grade 11 waves chapter, superposition theorem, how the two waves coincide and you get crest or trough. In the same way, one point or one charge you have to consider and then effect of all other charges on that point. So this is in accordance with the superposition principle. Now, I will consider this Q1, Q2 and Q3 from the point O. We will mention it as R1 vector, this as R3 vector, radius vector, this as R2 vector. Now I have to write the force experienced by this charge because of these two. Okay. So this will be Q R12. So now we will calculate the forces acting on this point charge Q1 due to Q2 and Q3. Okay. So it is like F12 force on Q1 due to Q2 is 1 by 4 pi epsilon naught Q1 Q2 divided by R12 square into R12 cap. Similarly, F13. So this will be in this direction. F13 will be in this direction. If we consider all our positive charges, we will consider the simplest way where you have repulsion taking place. So it is 1 by 4 pi epsilon naught Q1 Q3 divided by R13 square into R13 cap. These two charges only we have. If we consider some other charges, you have to consider that also. So this is what the superposition principle is. Only one at a time and effect of others on that charge. Okay. So the total force F1 I will write. You have to add this one, addition of forces. So it is nothing but F12 plus F13 in vector notation. It is 1 by 4 pi epsilon naught Q1 Q2 divided by R12 square into R12 cap plus 1 by 4 pi epsilon naught Q1 Q3 divided by R13 square into R13 cap. So this is the total force due to Q1 and Q3. Okay. Now you have to add these two. I can take 1 by 4 pi epsilon naught and Q1 as common. Okay. So you get, I hope I'll erase this one. So just keep in mind the diagram. You have these charges where the forces are acting. Okay. So now F1 will be equal to 1 by 4 pi epsilon naught into Q1 into Q2 divided by R12 square into R12 cap plus Q3 divided by R13 square into R13 cap. So in general, if I have n number of charges, out of that if I consider the effect of all other charges on the charge Q1, How will I write in a generalized notation? So it is vector F1 is equal to 1 by 4 pi epsilon naught Q1 summation of Qi divided by R1I square into R1I cap, where I running from, it's not 1, it is from 2. So you can notice here it is starting from 2. If you take 2 outside, Q1 will be here, Q3 will be here, like that. Okay, so I is equal to I from 1 to n. So this is the generalized notation of Coulomb's law when we deal with the multiple charges. I hope this is clear. So first you have to consider only one charge at a time according to the superposition principle, and then effect of all other charges on that charge, so that you get this notation. So our cap is very important, unit vector, and it is the force acting. Okay. So next topic is electric field. These directions are very important when we deal with the numericals, which we will solve once I finish this theory part. Electric field represented as E. Now if I have any point charge in vacuum, say it as Q at any one point in vacuum, it will have its own area wherein if you bring any other charges, they start interacting each other. Okay? So that is known as electric field. It is its own area where it can exert force on other particles or any other charges which you consider. Suppose if I bring any positive charge Q, in the surrounding region of this charge Q, then the plus Q will experience a force, by this charge Q. So now this is called as source charge, which produces the field around it, and this is called as test charge. Source charge and the test charge. Now you might have a question, why don't this plus Q will experience a force due to this one? Sorry, why don't this Q will experience a force due to plus Q? It will experience, but usually in our area of discussion, what we consider is this plus Q is so minute that we write limit tending to 0. It is not 0, because if you consider in our discussion, if you consider this as a greater charge, then dealing with the interaction by these two charges find it difficult. So what is done universally is we consider this as a very minute charge. It is so small that it is tending to 0. So such a minute charge we are considering, so that there is no effect on this charge due to the test charge. So this one you have to just keep in mind, that test charge is very small charge which we are considering. So now when I represent this E of R, R means a radial vector where we keep the source charge. So it is given by the same one, only a very small change, 1 by 4 pi epsilon naught. Now this come into picture. If you are keeping in vacuum, you have to consider as naught, epsilon naught, absolute permittivity of free space, Q divided by R square. So this Q we are considering. What Q you are taking as the source charge, that has to be considered. Now because of this, when you bring the test charge, this will experience the force. Correct? So the region around the test source charge will produce or will have the effect of force, which is experienced by some other charges when you bring it closer. So now it is nothing but force. Okay. The charge which you are bringing, Q into E. So you are multiplying the charge with the electric field, then you get the force experienced. So now you will get the expression for force. How can you write the expression? So it is 1. So now how can you define the electric field? Because of this force experienced by the point charge plus Q, you can define the electric field. So electric field, if this is a unit positive charge, what happens? Then this E will becomes equal to F. That is, electric field will becomes equal to force experienced by the unit charge. So electric field can be defined as the force experienced by the unit charge when placed at that particular point. So if you bring the unit test charge near the source charge, then the force experienced will be equal to the electric field. So that is how you define the electric field. Now some 4 points can be inferred from this equation. F is equal to Q into E. One is how you define the how you define the electric field E of R, if I write it in the vector form. Next one is, as I have already informed, that this Q will also experience some force due to the test charge. Now when we deal, it is very difficult to deal the two-way interaction. So we consider it as the force experienced is equal to limit Q tending to 0 of E by Q. So force experienced by this will be neglected if we consider very small test charge, that is limit Q tending to 0. Next, third point is, if I have the positive test charge or plus Q charge, how are the electric field lines? Or how is the electric field? Electric field lines we will study later. What about the direction of the electric field? So if it is plus Q, then electric field will be radially outwards. It is outwards, like this. That means if I bring any charge plus here, electric field will direct outwards. If I have negative charge as the source charge, then it will not be outwards, it will be towards. It is attractive in nature. Okay, minus Q. So this is plus Q and minus Q. How is the direction of the electric field, which is very important for the numericals. At the end you have to infer how is the direction of the net electric field. So if it is total negative, if you get, it is towards itself, and positive, if you get, it is away from that particular point. So this is the third point which we can infer from this equation. The last point is, as you go away from the point source or the source of this electric field, this is the third one. Now the fourth one, as you go away, the electric field goes on decreasing. As you know, it is inversely proportional to R square. But even though if you keep on increasing plus Q or the amount of test charges, the electric field is independent, because as the Q increases, or if you increase the distance, the F by Q will remain constant, the force. So that means you have say that electric field is independent of the charges or the test charges which you bring. The last one is, it is spherical in nature, because as you move away, if you consider the point charge, you can see from this diagram, plus Q if I consider, as you move away, its strength goes on decreasing. So the total field will be spherical in nature. If you consider the point, how is the shape? Just an imagination. It will be in a spherical form. Okay? The field, if you consider the electric field. So now, as you go away, its strength goes on increasing. Now, if I deal with the electric field due to multiple charges, again you have the same concept. electric field due to system of charges. Consider the point P. Here you have Q1, you have Q2, Q3 and Q4. Now at this point you have to calculate the total electric field due to all these charges Q1, Q2, Q3 and Q4. Okay. So now at this point P, E1, I will write it as R1P, R2P, these are the radius vectors, R3P, radial vectors, R4P. So now this will be E1P. E1P in this direction. We say that it is E2P. This will be E3P. This will outwards E4P. Now you have to consider the resultant vectors. If you want to consider the resultant vectors, you have to consider the parallelogram again. So now in this case you have to complete this parallelogram and this will be the, like this you will get the resultant. Here also in the same way complete the parallelogram. So according to the law of, this is this one. So E2 and E3P. So here you have to consider, here you get the resultant. So in the same way you have to calculate the total electric field as how you have calculated the forces on this point charge P. Now E1 I can write it as 1 by 4 pi epsilon naught Q1 divided by R1P square into R1P cap. Similarly E2 1 by 4 pi epsilon naught Q2 divided by R2P square into R2P cap. And then E3, vector E3 because of the charge Q3 is 1 by 4 pi epsilon naught Q3 divided by R3P square into R3P cap. Similarly E4 will be equal to 1 by 4 pi epsilon naught Q4 divided by R4P square into R4P cap. Now you have to consider the total or what is the net electric field at this point due to Q1, Q2, Q3 and Q4. You just have to add the charges. So now how you will add the charges? I hope I will erase this one. E1 plus E2 plus E3 plus E4 is equal to 1 by 4 pi epsilon naught is common. I will take it outside. So it is Q1 divided by R1P square into R1P cap plus Q2 divided by R2P square into R2P cap plus Q3 divided by R3P square into 3P cap, Q4 divided by into R4P cap. So similar how we have written the force in the generalized notation, same way I can write it as 1 by 4 pi epsilon naught into Qi divided by RIP square into RIP cap summation I moving from 1 to n. So this is the generalized notation vector E, where I moving from 1 to n if I have n number of charges. So Qi divided by RIP square you have to add into multiply by its unit vector. So this gives the electric field due to a system of charges. So first we have considered only the electric field, how we can represent the electric field. If you have positive charge, the field lines are outwards. If it is negative charge, it is attractive in nature. And then 4 points. First one is how you define the electric field. So it is that force which when you bring the unit positive charge at that point. Second point was limit Q tending to 0 of E by Q. So it is a force experience. Third one will be how if there is the direction of field, electric field, plus Q or minus Q, the same thing. Fourth one is it is a spherical in nature. The electric field will be spherical in nature, in the sense for the point charge or the point source charge, if you consider, it is radially outwards. So as you move away from the source charge, the strength of that will go on decreasing. So now how you can define the strength of the source charge? That is due to the field lines. So after electric field, you have the concept of field lines. Field lines will give the strength of the electric field. Now for that to define, or how you can measure the strength of the electric field, you have relative density concept. You have to consider the solid angle. In that, if you consider the relative density of the field lines, then you get to know the strength of the electric field at that particular point where you want to consider. So now next topic is electric field lines. Electric field lines. So now if I have any solid angle, what do you mean by solid angle? Solid angle is when you consider any cone shape, three-dimensional. In the circle you have radian, correct? Radians, how you measure the angle at the center. So it is a radians. So arc length will be equal to radius into the angle subtended at that particular point. Suppose you have any circle like this. If you want to find this one, this theta, if it is r, so you have S is equal to r into theta, correct? In the same way, when we go with the three-dimensional concept, you have angle subtended by the cone. Okay? This one, radian also we call. So it is angle subtended by the cone. So it is a radial vector. Suppose you consider this one. Say that you have the electric field lines like this. Now you can note that the field lines, if you consider 1, 2, 3 as the field lines, electric field lines due to the source charge Q, then you can see that here the field lines will be closer, and as it moves away or it goes away from this charge, it goes wider and wider. So if I represent this angle as delta omega, so it is the angle subtended by the cone, so delta omega, very very small angle. So you have to consider in each case and keep any one surface area here or here. Same surface area you have to consider. Say that this is S1 and S2. So the number of electric field lines passing through any surface which is held perpendicular to the electric field gives you the relative density concept. So that means you can note down here, if S1 and S2 are the surface areas of this shape, okay, same areas if you have considered, but different blocks, different places, say that this is at R1 and this is at R2 from this charge, then you can see clearly that here there are two field lines. Excuse me. Here there is one. So as you go away from the source charge, the strength of the field goes on reducing. So it is actually square times it is reducing. You have seen in the equation Q by R square. So square of that inversely proportional to square of the distance. So here field lines will be closer. As you go away, field lines are separated. Okay. So this is about the electric field lines. So you have to know the concept of relative density. Relative density means number of field lines passing through this areas if you consider. Okay. So that is the relative density. You have to consider equal surface areas. Then near the source charge you have closer field lines. As you go away you have the separated field lines. So this is about the electric field lines, which tells you about the strength of the electric field at that particular point.